Welcome to DAR Tutors. Today, we will explore the fundamental principles of electrochemistry at an IB higher level. By the end of this session, you will be able to predict the spontaneity of redox reactions using standard electrode potentials, represent voltaic cells using cell notation, calculate standard cell potentials, determine the products of electrolysis in aqueous solutions, and apply the concepts of Gibbs energy and Faraday's laws to solve electrochemical problems. Our learning objectives for this topic are as follows. First, to understand how to predict the spontaneity of a redox reaction. Second, to be able to calculate standard cell potentials. Third, to correctly represent voltaic cells using standard notation. Fourth, to learn how to determine the products of electrolysis in aqueous solutions. And fifth, to apply the relationships between cell potential, Gibbs energy, and Faraday's laws to perform calculations. We begin by predicting reactions at the electrodes. The key here is the standard electrode potential, E0. The half cell with the more positive or less negative, E0 value is the stronger oxidizing agent and will therefore undergo reduction. Conversely, the half cell with the more negative or less positive E0 value is the stronger reducing agent and will undergo oxidation. Let's formalize this. The electrode where oxidation occurs is called the anode, and it is the negative terminal. Here, electrons are released. The electrode where reduction occurs is called the cathode, and it is the positive terminal. Here, electrons are consumed. This is a crucial distinction for understanding electron flow in a voltaic cell. A useful mnemonic is oil rig. This stands for oxidation is loss. Reduction is gain. It reminds us that oxidation is the loss of electrons and reduction is the gain of electrons. Remember this rule. Reduction always occurs at the cathode and oxidation always occurs at the anode. Now, let's look at how to calculate the standard cell potential, E0 cell. It's the difference between the standard electrode potentials of the cathode and the anode. The formula is E0 cell equals E0 cathode minus E0 anode. This will always give you a positive value for a spontaneous reaction. It's also sometimes written as E0 cell equals E0 RC minus E0 LAH, referring to the right-hand and left-hand electrodes in a cell diagram. A critical top tip for your IB exams. Do not change the sign of the anode's standard electrode potential in the calculation. The negative sign in the formula E0 cathode minus E0 anode accounts for the sign change automatically. In other words, if the potential for a reduction reaction is negative, like that of magnesium, you substitute that negative value directly into the formula. The formula handles the sign conversion for the oxidation that occurs at the anode. Let's work through a step-by-step example to see this in action. The objective here is to deduce the ionic equation and standard cell potential for a spontaneous reaction. Consider a voltaic cell constructed from magnesium and copper electrodes under standard conditions. We are given the standard reduction potentials. Step 1. Identify the cathode and anode. To do this, we compare the standard electrode potentials. Copper has a potential of plus 0.34 volts, while magnesium has a potential of minus 2.37 volts. Since plus 0.34 is more positive than minus 2.37, the copper half cell is the cathode, where reduction takes place. Consequently, the magnesium half cell is the anode, where oxidation takes place. Step 2. Write the balanced half equations. Remember, the cathode undergoes reduction and the anode undergoes oxidation. At the cathode, copper-2 ions gain 2 electrons to form solid copper. At the anode, solid magnesium loses 2 electrons to form magnesium-2 ions. Step 3. Combine the half equations to get the overall ionic equation. We need to balance the number of electrons. In this case, both half reactions involve 2 electrons, so they balance out directly. Adding the 2 half equations gives us the net ionic equation. Solid magnesium plus copper-2 ions reacts to form magnesium-2 ions and solid copper. Notice how the electrons are cancelled out. Step 4. Calculate the standard cell potential. We use our formula E0 cell equals E0 cathode minus E0 anode. Substituting the values, we get plus 0.34 volts minus 2.37 volts. This calculation gives a result of plus 2.71 volts. The cell potential of plus 2.71 volts is positive, which is a key indicator. A positive cell potential confirms that the reaction we've written, where magnesium oxidizes and copper-2 ions reduce, is spontaneous under standard conditions. This completes our worked example. Now, let's look at another type of problem, calculating the standard electrode potential of an unknown half cell. Our objective here is to use a known cell potential to find a missing electrode potential. A voltaic cell is made from a cobalt half cell and a copper half cell. The overall cell potential is plus 0.62 volts, and we are told the copper half cell is the positive one. Step 1. Identify the cathode and anode from the information given. Positive electrode is just another name for the cathode. Therefore, the copper half cell is the cathode. Consequently, the cobalt half cell must be the anode. This is a crucial first step. Misidentifying the roles will lead to an incorrect answer. Step 2. Recall the formula for standard cell potential and plug in the known values. The formula is E0 cell equals E0 cathode minus E0 anode. We know E0 cell is plus 0.62 volts. From the IB chemistry data booklet, the standard reduction potential of copper is plus 0.34 volts. Let's call the unknown potential of the cobalt half cell X. Step 3. Solve the equation for X. This is a simple algebraic manipulation. Subtract 0.34 from both sides to isolate X, giving us 0.28 equals X. Therefore, X, the standard reduction potential for cobalt, is 0.28 volts. The standard electrode potential of the cobalt half cell is pure 0.28 volts. The negative sign confirms that cobalt is more easily oxidized than hydrogen, which is consistent with its role as the anode in this cell. Now we will learn a new skill, representing an electrochemical cell with a compact notation, often called a cell diagram or cell notation. The objective is to convert a description of a cell into this standard notation. Let's break down the rules for this notation. It's always anode on the left, cathode on the right. A single vertical line represents a phase boundary, for example, between a solid metal electrode and its aqueous ion solution. A double vertical line, known as a salt bridge, separates the two half cells and allows ion flow. Reactants for a half cell are on the electrode side, and products are on the salt bridge side. Let's apply these rules to an example. Represent the cell obtained by combining copper and silver half cells. Step 1. Determine which is the anode and which is the cathode. We compare the standard electrode potentials. Silver's potential of plus 0.80 volts is more positive than copper's plus 0.34 volts. This means silver is the cathode and will be reduced, while copper is the anode and will be oxidized. Step 2. Construct the cell diagram using the established rules. Anode on the left, cathode on the right, separated by a salt bridge. Starting with the anode on the left, we write solid copper, a phase boundary, and then the copper-2 ion solution. Then comes the double line for the salt bridge. On the cathode side, we write the silver ion solution, a phase boundary, and finally the solid silver electrode. This represents the entire cell. We will now explore the fundamental relationship that connects electrochemistry to thermodynamics. The objective is to understand how the standard cell potential, E0 cell or aqua cell, relates to the standard Gibbs energy change, delta G0. For a spontaneous process, the standard Gibbs energy change, delta G0, must be negative. The more negative the delta G0, the more spontaneous the reaction. Conversely, for an electrochemical cell to be voltaic, or spontaneous, its standard cell potential, E0 cell, must be positive. This direct opposition suggests a quantitative link. The maximum amount of electrical work that can be done by a spontaneous electrochemical cell is equal to the Gibbs energy change. This relationship is described by the equation delta G0 equals negative NF E0 cell. Let's define the terms. Delta G0 is the standard Gibbs energy change in joules per mole, and is the amount of electrons in moles transferred between the electrodes as shown in the balanced cell reaction. F is the Faraday constant, which is 96,500 coulombs per mole, and E0 cell is the standard cell potential in volts. This equation shows that a positive E0 cell results in a negative delta G0, confirming spontaneity. Let's apply this to a well-known voltaic cell. In the Daniell cell, zinc metal reacts with copper-2 ions. The half reactions and overall reaction are shown. The standard cell potential for this cell is plus 1.10 volts. Step 1. Determine N, the moles of electrons transferred. From the half equations, we can see that 2 moles of electrons are transferred for every mole of reaction. So N equals 2. Now we have all the values to calculate delta G naught. Step 2. Calculate delta G naught using the equation. Substituting the values, we get delta G D. G naught equals negative 2 times 96,500 coulombs per mole times 1.1 volts. This calculates to negative 212,300 joules per mole, or approximately negative 212 kilojoules per mole when rounded to 3 significant figures. This large negative value for delta G naught confirms the Daniell cell is thermodynamically spontaneous, and the process would release 212 kilojoules of energy per mole of zinc consumed, which is then converted into electrical work. It is crucial to understand the limitations of thermodynamic predictions. The objective of this scene is to distinguish between thermodynamic feasibility, which is described by delta G naught and E naught, and kinetic feasibility, which determines the rate of a reaction. Thermodynamics, which we've been discussing with delta G naught and E naught, tells us if a reaction is energetically possible, but it says nothing about how fast it will occur. A positive cell potential, E naught cell, indicates a thermodynamically favorable reaction. It should proceed spontaneously. However, the reaction might have a very high activation energy. If the activation energy is high, the reaction will be extremely slow, perhaps immeasurably so, under normal conditions. In such cases, we describe the reaction as being thermodynamically favorable but kinetically unfavored. It wants to happen, but it just can't get started. Let's consider a classic example. Consider the reaction between hydrogen gas and aqueous copper-2 ions. We calculate the standard cell potential for this reaction. The copper half cell has a reduction potential of plus 0.34 V. The hydrogen standard electrode has a potential of 0.10 V. So E naught cell is plus 0.34 V minus 0.20 V, which equals plus 0.34 V. Since this value is positive, the reaction is thermodynamically spontaneous. The thermodynamics tell us that hydrogen gas should displace copper from a copper-2 sulfate solution. However, in practice, no copper is formed, and the hydrogen gas simply bubbles through the solution. Why? The reason is kinetic. Hydrogen molecules have a very strong covalent bond. A significant amount of energy is required to break this bond so that the hydrogen atoms can react. This high activation energy makes the reaction rate exceptionally slow, rendering the thermodynamically favorable reaction kinetically unfeasible. This example perfectly illustrates that a positive E naught cell or a negative delta G naught is a necessary but not sufficient condition for a reaction to occur at a noticeable rate. So far, we have only discussed electrochemical cells under standard conditions. But what happens if the concentrations of the ions involved are not 1 mole per decimeter cubed? The objective here is to understand how non-standard conditions, specifically changes in concentration, affect cell potential. When the concentrations are not standard, the cell potential E naught cell will change. We can predict the direction of this change using Le Chatelier's principle. Consider a generic reduction equilibrium for a species OX. If we increase the concentration of the reactant, the oxidized species OX, the equilibrium will shift to the right to relieve the stress. This shift towards reduction makes the potential of that half cell more positive. Conversely, decreasing the concentration of OX or increasing the product, red, shifts the equilibrium left, making the potential less positive. This qualitative prediction is refined by a quantitative tool. The Nernst equation allows chemists to calculate the cell potentials of non-standard cells. It describes the precise relationship between cell potential, E, standard cell potential, E naught, and the concentrations of the species involved, which are grouped into the reaction quotient, Q. Let's apply this to our Daniell cell. We know the Daniell cell has a standard potential of plus 1.10. Fe. The overall ionic equation is zinc plus copper-2 ions to produce zinc-2 ions plus copper. Now let's consider what happens if we change the ion concentrations. If the concentration of copper-2 ions is increased and the concentration of zinc-2 ions is decreased, what happens to the potential? The reaction quotient Q, which is Zn2 plus Cu2 plus, becomes smaller. This makes the log term negative. The Nernst equation becomes E equals 1.10, a negative number. So the cell potential, E, increases to a value greater than 1.7 V. The cell can do more work. This aligns with Le Chatelier's principle. Increasing the reactant Cu2 plus and decreasing the product Zn2 plus shifts the equilibrium to the right, increasing the driving force. Conversely, if we decrease the concentration of copper-2 ions and increase the concentration of zinc-2 ions, the reaction quotient Q becomes larger. This makes the log term positive. The Nernst equation becomes E equals 1.10, a positive number. The cell potential, E, decreases to a value less than 1.10 of V. This also aligns with Le Chatelier's principle. Favoring the products shifts the equilibrium left, decreasing the spontaneity in the cell potential. The Nernst equation is a powerful tool for analyzing electrochemical cells under any conditions. We now shift our focus from spontaneous voltaic cells to non-spontaneous electrolytic cells. The objective is to understand how to predict the products of electrolysis in aqueous solutions. In an aqueous solution, we have both the ions of the electrolyte and water molecules present. These species compete to be reduced at the cathode and oxidized at the anode. Water itself can be electrolyzed. The oxidation of water at the anode produces oxygen gas, hydrogen ions, and electrons. The reduction of water at the cathode produces hydrogen gas, hydroxide ions, and electrons. This competition is the key to understanding electrolysis. To determine the products, we need a set of rules. Rule 1. At the cathode, the cation that has the most positive reduction potential will be reduced. If the metal cation is more reactive than hydrogen, its reduction potential is very negative, so water will be reduced instead, producing hydrogen gas. Rule 2. At the anode, it's the opposite. The species with the most negative reduction potential, meaning it's most easily oxidized, will be oxidized. So, it's about being the strongest oxidizing agent at the cathode and the strongest reducing agent at the anode. One crucial exception is concentration. For halides like chloride, ions, the standard electrode potential suggests water should be oxidized first. However, if the concentration of the halide is high, the high number of collisions overcomes the kinetic barrier, and the halide ion is oxidized preferentially. This is particularly important for concentrated versus dilute NaCl solutions. Let's apply these rules to a few examples. First, the electrolysis of dilute aqueous sodium chloride. At the cathode, we compare the reduction of Na plus in water. Water has a more positive potential, 0.83 V versus 2.71 V, so water is reduced, producing hydrogen gas. At the anode, we compare the oxidation of Cl in water. Water is more easily oxidized, 0.23 V versus plus 1.36 V, producing oxygen gas. Now the electrolysis of concentrated aqueous sodium chloride. The cathode reaction is the same. Water is reduced to hydrogen gas. However, at the anode, because the Cl ions are highly concentrated, they are oxidized in preference to water. We get chlorine gas instead of oxygen gas. Finally, the electrolysis of aqueous copper-2 sulfate. At the cathode, we compare Cu2 plus and water. Cu2 plus has a much more positive potential, plus 0.34 V versus 0.83 V, so it is reduced to solid copper. At the anode, water is more easily oxidized than the sulfate ion, producing oxygen gas. We will now discuss the quantitative aspects of electrolysis as established by Michael Faraday in his historic experiments. The objective is to understand and apply Faraday's two laws of electrolysis. In 1833, Michael Faraday summarized his careful measurements of the masses of substances produced at cathodes during electrolysis. He formulated two laws. Faraday's first law states that the mass of an element produced is directly proportional to the quantity of electricity or charge passed through the cell. The total charge, Q, is simply the product of the current in amperes, I, and the time in seconds, T. The units are coulombs, amperes, and seconds. Faraday's second law is a comparison. It states that the masses of different elements produced by the same quantity of electricity form simple whole number ratios when divided by their relative atomic masses. In other words, if you use the same total charge in two different electrolytic cells, the amount of moles of each substance produced is inversely proportional to its charge. In modern terms, these laws simply state that the amount of a substance produced at an electrode is directly proportional to the number of moles of electrons transferred. The number of moles of electrons transferred to discharge 1 mole of an ion is equal to the magnitude of the ion's charge. Let's demonstrate this with an example. Aqueous solutions of copper-2 sulfate and chromium-3 nitrate are electrolyzed using the same quantity of electricity. The question asks us to compare the amounts of metal atoms produced. Since the quantity of electricity, Q, is the same for both, the number of moles of electrons, Ne, is also the same. Let's assume that any moles of electrons are passed. The reduction of copper-2 requires 2 moles of electrons to produce 1 mole of copper. The reduction of chromium-3 requires 3 moles of electrons to produce 1 mole of chromium. Therefore, the number of moles of copper produced is 1/2 of Ne, and the number of moles of chromium produced is 1/3 of Ne. This clearly shows that more copper is produced than chromium for the same amount of charge. The ratio of moles of copper to moles of chromium is 1/2 to 1/3, which is 3 to 2. This demonstrates Faraday's second law. The amount of product is inversely proportional to the charge of the ion. Finally, let's explore a practical application of electrochemistry called anodizing. The objective is to understand what anodizing is, how it works, and why it is a useful process for metals like aluminum. Anodizing is a process that coats a metal object with a layer of its own oxide. As the name suggests, the metal to be coated is made into the anode of an electrochemical cell. This process is most famously used for aluminum. In anodizing aluminum, a carbon cathode is placed in an electrolyte, often sulfuric acid, along with an aluminum anode. When a current is applied, water is reduced at the cathode, producing hydrogen gas. At the aluminum anode, the aluminum metal is oxidized, forming aluminum oxide, Al2O3, which coats the surface. Anodizing is an effective way to protect aluminum for several reasons. First, the aluminum oxide layer is much harder and more durable than the original aluminum, increasing its wear resistance. Second, this oxide layer is highly corrosion resistant, protecting the underlying aluminum from chemical attack and atmospheric corrosion. Third, the oxide layer is porous, allowing organic dyes to permeate it. These dyes get trapped as the layer hardens, allowing for a wide range of attractive, durable colors. There are also other benefits. The thickness of the coating can be precisely controlled by varying the current and the time of electrolysis. The porosity can also be controlled by adjusting the conditions. This process allows manufacturers to produce aluminum objects with tailored properties, such as anodized bicycle parts in various colors. The anodizing of aluminum is an excellent example of how the principles of electrochemistry can be used to create materials with enhanced properties for diverse applications. We will now conclude this session with a call to action. We have covered several key topics in IB chemistry higher level, from calculating cell potentials and predicting spontaneity to the nuances of electrolysis, the relationship with Gibbs energy, and the practical application of anodizing. These are complex concepts that require practice and a deep understanding of the underlying principles. If you found this session helpful but still feel you could benefit from more personalized, in-depth support, then DAR Tutors is here to help. We offer expert online and home tuition for students studying IB A-Level and IGCSE curricula. Our experienced tutors can provide the targeted support you need to master these challenging topics and achieve your academic goals. Whether you need help with the fundamental theory, problem-solving strategies, or preparing for your exams, DAR Tutors can provide a bespoke learning experience designed just for you. Contact us today to learn more. To help solidify your understanding and prepare you for your IB exams, let's work through 5 practice questions. These are designed to test your knowledge of the concepts we have covered today. I encourage you to pause the video after each question, attempt it yourself, and then watch the detailed solution. Question 1 asks us to identify the anode and cathode and calculate the standard cell potential for a voltaic cell made from magnesium and silver electrodes. To solve this, We first need the standard electrode potentials. From the data booklet, the standard reduction potential for magnesium is minus 2.37 volts, and for silver, it's plus 0.80 volts. Step 2 is to compare these potentials to determine the anode and cathode. Silver's potential of plus 0.80 in V is much more positive than magnesium's, 2.37 so V. Therefore, the silver half cell is the cathode, where reduction occurs, and the magnesium half cell is the anode, where oxidation occurs. Step 3 is to use the formula for standard cell potential. E naught cell equals E naught cathode minus E naught anode. Substituting the values gives plus 0.80 V minus 2.37 V, which calculates to plus 3.110 V. A positive value of plus 3.17 volts confirms that this cell is voltaic and the reaction is spontaneous. Question 2 asks for the value of the standard Gibbs energy change delta G naught for the magnesium-silver cell we just analyzed. To solve this, we will use the equation connecting cell potential and Gibbs energy. The equation is delta G naught equals negative NF E naught cell. From our previous calculation, we know E naught cell is plus 3.11 V. The key is to determine N, the moles of electrons transferred. The half equations are: magnesium oxidizes to Mg2+, releasing 2 electrons. Silver ions reduce to solid silver, gaining 1 electron. To balance the electrons, we must multiply the silver reduction by 2. This gives a total of 2 electrons transferred, so N equals 2. Now we have all the values to calculate delta G naught. Plugging them into the formula, we get delta G naught equals negative 2 times 96,500 times 3.1 seen, which equals negative 611,620 joules per mole. Converting this to kilojoules gives negative 611.62 kilojoules per mole. The large negative value of delta G naught confirms the high spontaneity of this reaction and the large amount of electrical work it can perform. Question 3 is about predicting electrolysis products. We need to identify what gases are formed when dilute aqueous hydrobromic acid is electrolyzed using inert electrodes. First, let's identify all the species present in the solution. We have H+ ions from the acid, Br- ions from the acid, and H2O molecules, which are always present in an aqueous solution. Next, let's look at the cathode. The cathode is the site of reduction. We have 2 potential candidates for reduction: H+ ions and water molecules. Consulting the IB data booklet, the standard reduction potential for H+ is 0.00 volts, and for water, it is negative 0.83 volts. Since 0 is more positive, H+ ions are more easily reduced. The reaction at the cathode will be 2H+ plus 2 electrons to form H2 gas. The product is hydrogen gas. Now let's consider the anode, the site of oxidation. The candidates for oxidation are Br- ions and water molecules. When comparing their reduction potentials for oxidation, we look for the more negative value, as this corresponds to the strongest reducing agent. The reduction potential for water to oxygen is negative 1.23 volts, and for bromine to bromide, it's plus 1.09 volts. Therefore, water is more easily oxidized than bromide. The anode reaction is 2H2O to form O2 gas, 4 H+ ions, and 4 electrons. The product is oxygen gas. Therefore, the gases produced are hydrogen gas at the cathode and oxygen gas at the anode. Question 4 combines Faraday's first law with stoichiometry. We are asked to calculate the time required to deposit a certain mass of metal. To solve this, we need to connect the mass of silver to the moles of electrons, then to the total charge, and finally to the time. Step 1 is to find the moles of silver deposited. We divide the given mass by the molar mass of silver, which is 107.87 gkg mole. This gives us 0.0139 moles. Step 2 is to find the moles of electrons required. The half reaction for silver deposition is Ag plus E gives Ag. This shows a 1:1 molar ratio. Therefore, the moles of electrons needed are equal to the moles of silver, which is 0.0139 moles. Step 3 is to find the total charge. We use the Faraday constant, F, Charge equals moles of electrons times the Faraday constant. So 0.00139 moles times 96,500 coulombs per mole gives a total charge of 134235 coulombs. Step 4 is to find the time in seconds. We use the formula Q equals I times T. Rearranging for T, we get T equals Q over I. So 11342.35. Coulombs divided by 0.800 amperes gives 1677.9 seconds. The question asks for the answer in minutes. We just need one more conversion. Dividing 1677.9 seconds by 60 gives approximately 27.97 minutes. So, the electrolysis ran for about 28 minutes to deposit 1.5 grams of silver. Our final question is a conceptual one, testing your understanding of the Nernst equation and Le Chatelier's principle. We are asked to explain why increasing the concentration of Fe3+ ions in the anode compartment of a galvanic cell would increase the cell's voltage. Let's assume the iron half cell is the anode, which means it's undergoing oxidation, not reduction. So the reaction at the anode is the oxidation of iron 2 ions to iron 3 ions, releasing one electron. If we increase the concentration of Fe3+, that is, the product of this half reaction, Le Chatelier's principle tells us the equilibrium will shift to the left to consume the excess product. A shift to the left means the system is favoring the formation of the reactant, Fe2+. It is resisting the oxidation process. This means that the electrons are being held onto more tightly by the iron species in that half cell. A shift to the left makes it more difficult for the iron to be oxidized, which means its tendency to release electrons, its reduction potential, becomes more negative. In a galvanic cell, a more negative anode potential increases the overall difference in potential between the two electrodes, resulting in a higher cell voltage. To be more precise, the Nernst equation for the iron half cell is shown. The reaction quotient Q is the concentration of oxidized species, Fe3+, divided by the concentration of reduced species, Fe2+. If we increase Fe3+, Q becomes larger, so the term 0.05921 times log Q becomes more positive. Subtracting this positive term from the standard potential makes the half-cell potential, EHFE, more negative. This increased potential difference is what boosts the cell's overall voltage. A more negative anode potential increases the overall E cell, as E cell, E source, E cathode, E anode. This confirms our initial prediction. Thank you for joining this session on electrochemistry. We've explored the fundamental concepts of voltaic and electrolytic cells, spontaneity, cell potential, Gibbs energy, Faraday's laws, and practical applications like anodizing. These topics form a crucial part of the IB higher level chemistry curriculum. Continued practice with the types of problems we've worked through today is essential for mastery. For more in-depth support and personalized guidance, remember to contact DAR tutors. Thank you for your time.